Nuclear pasta is one of those expressions that sounds like a metaphor, a joke, or a poetic exaggeration, yet it refers to something profoundly real, something that exists not in imagination but in the deepest, most extreme corners of the universe. When you first hear the phrase, it is easy to smile, to picture spaghetti drifting through space, or lasagna sheets floating among the stars. But nuclear pasta is neither playful nor abstract. It is a form of matter so dense, so strange, and so resistant that it challenges everything we think we know about physics, solidity, and the limits of nature itself. And the most astonishing part is that it exists right now, locked away inside the corpses of dead stars, quietly shaping the fate of some of the most extreme objects in the cosmos. To understand why nuclear pasta matters, we must begin by letting go of everyday intuition. In our daily lives, density is a simple concept. We compare wood to metal, air to water, stone to iron. Even the densest materials we handle, like lead or osmium, are tame compared to what the universe can produce under truly extreme conditions. Nuclear pasta exists in an environment where atoms are crushed beyond recognition, where electrons are forced into protons, where the distinction between individual particles begins to blur. It is matter pushed so far that it rearranges itself into shapes that seem almost biological, as if the universe itself were experimenting with form. At the heart of this story are neutron stars. These objects are born in violence. When a massive star runs out of fuel, it can no longer support itself against gravity. The core collapses in a fraction of a second. Protons and electrons merge into neutrons, and the outer layers explode outward in a supernova. What remains is a neutron star, an object with a mass greater than the sun packed into a sphere barely 20 kilometers across. A single teaspoon of neutron star material would weigh billions of tons on Earth. This is not an exaggeration. It is a literal statement of how extreme these objects are. Inside a neutron star, gravity and quantum mechanics engage in a relentless tug-of-war. Gravity wants to compress everything into a single point, while quantum forces resist total collapse. The result is a layered structure. Each layer is stranger than the last. Near the surface there is a crust made of atomic nuclei arranged in a lattice, immersed in a sea of electrons. Deeper down, nuclei become more neutron-rich, until eventually they dissolve into a soup of neutrons. It is in this transitional region, at the boundary between the crust and the core, that nuclear pasta forms. This region is extraordinary because it sits at a crossroads of competing forces. On one hand, the strong nuclear force tries to hold protons and neutrons together, favoring compact clustered structures. On the other hand, the electric repulsion between positively charged protons pushes matter to spread out. Add to this the crushing pressure of gravity, and you have a system that cannot settle for simple shapes like spheres. Instead, matter organizes itself into complex, repeating structures that minimize energy under these conflicting demands. Physicists discovered these structures not by direct observation, but through theory and simulation. When they modeled nuclear matter at the densities found in neutron star crusts, they noticed something remarkable. Instead of forming isolated nuclei, matter stretched, flattened, and twisted into shapes that resembled familiar types of pasta. Long cylindrical rods looked like spaghetti. Flat slabs resembled lasagna sheets. There were also more exotic forms like perforated slabs and tangled networks, earning names like gnocchi, bucatini, and Swiss cheese. These whimsical labels hide a profound reality. Matter at the edge of nuclear collapse arranges itself into some of the most complex structures known in physics. What makes nuclear pasta so fascinating is not just its shape, but its properties. According to current research, nuclear pasta may be the strongest material in the known universe. Stronger than steel, stronger than diamond, stronger than anything we can produce in a laboratory. Its strength comes from the way nuclear forces bind these structures together across enormous scales, relative to atomic dimensions. Cracks, which weaken materials on Earth, struggle to propagate through nuclear pasta because of its irregular, intertwined geometry. In a sense, it is matter that resists breaking by design, forged under conditions so extreme that weakness simply has no place to form. This incredible strength has real consequences for neutron stars themselves. Neutron stars are not perfectly smooth or static. They spin, sometimes hundreds of times per second, and their rotation gradually slows over time. Occasionally, a neutron star experiences a sudden change in its rotation rate, known as a glitch. These glitches are thought to be caused by interactions between the crust and the superfluid interior. Nuclear pasta residing at the boundary between these regions may play a crucial role in how stress builds up and is released. Its rigidity could allow stress to accumulate until it suddenly snaps, leading to observable changes in the star's rotation. Beyond rotation, nuclear pasta may also influence how neutron stars cool. Neutron stars lose heat primarily through the emission of neutrinos, nearly massless particles that can escape even the densest matter. The presence of nuclear pasta affects how electrons and neutrons move and interact, which in turn influences neutrino production. A star with a thick layer of nuclear pasta may cool differently from one without it, altering its thermal evolution over thousands or millions of years. In this way, an invisible structure buried deep inside a dead star can shape what we observe from across the galaxy. The study of nuclear pasta also blurs the line between nuclear physics and condensed matter physics. The shapes that emerge are reminiscent of patterns seen in soft materials, like foams, liquid crystals, and biological membranes. This similarity is not superficial in all these systems. Complex structures arise from simple rules when competing forces are balanced. In nuclear pasta, the balance is between nuclear attraction and electric repulsion. In biological systems, it might be between surface tension and elasticity. The universe, it seems, reuses its favorite strategies across vastly different scales. What makes this even more intriguing is that nuclear pasta is not static. At the temperatures present in young neutron stars, these structures may fluctuate, vibrate, and rearrange themselves. Over time, as the star cools, the pasta may freeze into more rigid forms. Understanding this behavior requires some of the most powerful supercomputers on Earth, capable of simulating millions of interacting particles under extreme conditions. These simulations are not just academic exercises. They are essential tools for connecting theory with astronomical observation. Despite all this progress, nuclear pasta remains elusive in one crucial sense. We cannot touch it, see it directly, or recreate it in a laboratory. The pressures and densities required are simply beyond our current technological reach. Even the most advanced particle accelerators can only probe fragments of the physics involved. As a result, nuclear pasta exists primarily as a theoretical and computational construct, supported indirectly by observations of neutron star behavior. It is real, but it lives at the edge of what we can test and verify. This limitation raises a deeper question about how we know what we know in modern science. Nuclear pasta is a triumph of inference. We observe neutron stars. We measure their masses, radii, spins, and emissions. We apply the laws of physics, tested under less extreme conditions, and extend them into regimes we cannot directly access. When these laws predict the existence of exotic structures like nuclear pasta, and when those predictions help explain what we observe, confidence grows. In this way, nuclear pasta becomes a symbol of how human knowledge stretches into the unknown, guided by logic, mathematics, and imagination. There is also something humbling about nuclear pasta. It reminds us that the universe is under no obligation to conform to our expectations or categories. The matter we encounter in everyday life is only a tiny subset of what is possible. Under different conditions, the same fundamental particles arrange themselves in radically different ways. The fact that protons and neutrons can form spaghetti-like rods or lasagna-like sheets is not a curiosity. It is a revelation about the flexibility and creativity of nature itself. As we push further into the era of multi-messenger astronomy, combining electromagnetic observations with gravitational waves and neutrinos, the importance of understanding neutron star interiors will only grow. When two neutron stars collide, as observed in gravitational wave events, their internal structures influence how they deform, merge, and ultimately collapse. Nuclear pasta, with its unique mechanical properties, may affect how these collisions unfold and what signals they produce. In this sense, pasta hidden deep inside a star can echo across the universe in ripples of spacetime. The story of nuclear pasta is still being written. Each new simulation, each new observation, adds another piece to the puzzle. What we have learned so far is already astonishing, but many questions remain unanswered. How thick is the pasta layer in typical neutron stars? How does it vary with mass and composition? Does it behave more like a solid, a liquid, or something in between? And are there even more exotic phases of matter waiting to be discovered deeper inside these stellar remnants? These questions are not just technical details for specialists. They touch on fundamental issues about matter, forces, and the ultimate limits of physical law. Nuclear pasta sits at a boundary, not only between the crust and core of a neutron star, but between the known and the unknown. It is a reminder that even in a universe we have studied for centuries, there are still regions where reality becomes strange enough to challenge our language, our intuition, and our imagination. And yet, perhaps that is what makes nuclear pasta so compelling. It is a bridge between the familiar and the alien, between kitchen table metaphors and cosmic extremes. It takes a humble concept like pasta and transforms it into a gateway to some of the deepest questions in astrophysics. In doing so, it invites us to keep watching, keep listening, and keep asking, because the universe is far stranger and far more fascinating than we ever assumed. To truly grasp how extraordinary nuclear pasta is, it helps to zoom in, far beyond human scales, and imagine what matter is enduring in that narrow layer of a neutron star. Here, density approaches that of atomic nuclei themselves. At these extremes, atoms no longer exist as we know them. Electron clouds are stripped away, nuclei are squeezed together, and the usual boundaries between particles begin to dissolve. Matter is no longer governed by chemistry, but by raw nuclear and quantum forces. This is the regime where intuition fails and mathematics takes over. In ordinary nuclei, protons and neutrons are held together by the strong nuclear force, one of the four fundamental forces of nature. It is incredibly powerful, but it only acts over extremely short distances. In neutron star crusts, however, nuclei are packed so closely that these forces begin to interact across neighboring clusters. At the same time, the positively charged protons repel each other electromagnetically. This competition creates frustration in the physical sense. The system cannot satisfy all forces simultaneously. When frustration dominates, complex patterns emerge. This phenomenon is not unique to neutron stars. Similar frustration-driven patterns appear in magnets, polymers, and even biological tissues, but nuclear pasta represents this principle taken to its absolute extreme. Instead of molecules or cells, the building blocks are protons and neutrons. Instead of soft forces, the interactions involve energies that dwarf anything encountered on Earth. The result is matter arranged in repeating, self-organized structures that minimize energy under impossible conditions. As density increases with depth inside the neutron star, the shapes of nuclear pasta evolve. At lower densities, matter forms isolated spherical clusters, often called nuclear gnocchi. These are remnants of traditional nuclei, still recognizable as roughly bold. As pressure increases, these spheres begin to merge into elongated rods, forming spaghetti-like structures that stretch across the crust. Deeper still, the rods fuse into flat sheets, lasagna-like slabs that extend for kilometers, relative to nuclear scales. Eventually, even these sheets break down into inverted structures, where voids form within dense matter, creating bubble-like configurations. What is astonishing is not only that these shapes exist, but that they are predicted consistently across different models and simulations. Researchers using entirely different computational approaches arrive at similar conclusions. This convergence suggests that nuclear pasta is not a theoretical curiosity, but an inevitable consequence of the laws of physics under extreme conditions. When matter is squeezed hard enough, complexity is not an exception. It is the rule. One of the most striking properties of nuclear pasta is its elasticity. Unlike brittle materials, which fracture easily, nuclear pasta can deform significantly without breaking. This behavior is rooted in the way its structures are interconnected. When stress is applied, the force is distributed across extended networks of nucleolines, rather than concentrated at a single weak point. This makes it extraordinarily resistant to shear and deformation, a quality that has profound implications for neutron star dynamics. This resistance may explain why neutron star crusts can sustain mountains, tiny deviations from perfect spherical symmetry. These mountains are minuscule by everyday standards, often only centimeters high, but on a neutron star they represent enormous masses displaced against gravity. Such asymmetries can generate continuous gravitational waves as the star rotates, ripples in space-time that detectors on Earth are only just beginning to search for. Nuclear pasta, by strengthening the crust, may allow these deformations to persist longer than previously thought. The connection between nuclear pasta and gravitational waves is one of the most exciting frontiers in modern astrophysics. If detected, these waves would carry information directly from the interiors of neutron stars, offering an unprecedented probe of matter at nuclear densities. In this context, nuclear pasta is no longer an abstract concept. It becomes a potential source of observable signals, a hidden architect shaping phenomena we can measure across cosmic distances. Another critical role of nuclear pasta lies in its interaction with particles that permeate neutron stars, particularly neutrinos. Neutrinos are elusive, nearly massless particles that interact weakly with matter, yet in neutron stars they dominate energy transport. The complex geometry of nuclear pasta can scatter neutrinos in unexpected ways, altering how efficiently they escape. This scattering affects how neutron stars cool, especially in their early life stages, when temperatures are extremely high. Cooling curves, which track how a neutron star's temperature decreases over time, are one of the primary observational tools available to astrophysicists. By comparing theoretical models with observed temperatures, scientists attempt to infer what lies beneath the surface. Nuclear pasta adds a layer of complexity to this effort. Its presence can slow cooling, trap heat, or redirect energy flow, meaning that even subtle changes in its structure could leave detectable signatures millions of years later. Despite its importance, nuclear pasta remains one of the least understood phases of matter. Simulating it accurately is a monumental challenge. The calculations must account for quantum mechanics, nuclear forces, relativistic effects, and immense numbers of particles, all interacting simultaneously. Even with modern supercomputers, researchers must make approximations and assumptions. Each simulation is a compromise between realism and feasibility, and interpreting the results requires caution and creativity. This uncertainty has sparked lively debate within the scientific community. Some models suggest that nuclear pasta occupies a relatively thin layer, while others propose it could extend much deeper into the star. Some predict highly ordered crystalline structures, while others favor more disordered, glass-like configurations. These differences matter because they influence everything from thermal conductivity to mechanical strength. The true nature of nuclear pasta may lie somewhere between these extremes, or it may surprise us entirely. What is clear is that nuclear pasta challenges the traditional distinction between solid and liquid. In some respects, it behaves like a solid, resisting deformation and supporting stress. In others, it flows or rearranges itself over long timescales, more like a viscous fluid. This duality places it in a category of its own, a reminder that the phases of matter we learn about in school are only a small subset of what the universe permits. There is also a philosophical dimension to nuclear pasta that is difficult to ignore. It exists in a realm we can never visit, inside objects that would destroy any spacecraft or probe long before reaching their interiors. Yet through mathematics and observation, we can describe its properties with surprising precision. This speaks to the power of human reasoning, but also to its limits. We can model nuclear pasta, name it, and debate it, but we must accept that our understanding will always be indirect, filtered through layers of theory and inference. Still, these indirect insights have real consequences. They shape how we interpret astronomical data, how we design future detectors, and how we refine our theories of matter. Nuclear pasta is a bridge between microphysics and astrophysics, linking the behavior of individual nucleons to the evolution of stars and galaxies. Few concepts span such a vast range of scales, from femtometers to light years with such coherence. As research continues, nuclear pasta may also inform other areas of physics. The mathematical tools developed to study it are being applied to complex systems far removed from astrophysics, from materials science to data networks. In this sense, the extreme conditions of neutron stars serve as a laboratory not just for understanding the universe, but for discovering principles that apply across disciplines. And yet, for all its complexity and importance, nuclear pasta remains hidden, silent, and inaccessible. It does not emit light. It does not announce its presence directly. It influences the universe subtly, through strength, structure, and interaction. This quiet influence is part of its mystery and its appeal. It reminds us that some of the most consequential features of reality are not the ones that shine the brightest, but those that endure the greatest pressure. As we move deeper into the story of nuclear pasta, the questions become even more profound. What happens to these structures over billions of years? Do they evolve, crack, or melt as neutron stars age? And what role do they play in the most violent events in the universe, when neutron stars collide or collapse? To answer these questions, we must push further, beyond the crust, beyond current models, and closer to the very limits of physics. When neutron stars are left alone, nuclear pasta exists in silence, compressed and hidden beneath layers of matter that defy imagination. But the universe rarely leaves its most extreme objects undisturbed. Over cosmic timescales, neutron stars can drift into binary systems, locked in slow, inevitable spirals toward one another. When this happens, nuclear pasta is no longer just a passive structure. It becomes an active participant in some of the most violent and energetic events known to science. As two neutron stars orbit closer, tidal forces begin to stretch and strain their crusts. The immense gravitational pull each star exerts on the other creates stresses far beyond anything experienced by terrestrial materials. In these moments, the strength of nuclear pasta is put to the ultimate test. The crust deforms, resists, and eventually fractures. How and when this happens depends critically on the properties of nuclear pasta buried within. If nuclear pasta is as strong as simulations suggest, it can delay crust failure, allowing stress to build to extraordinary levels. When the crust finally breaks, the release of energy can be sudden and immense. This process may influence the precise timing and structure of gravitational wave signals emitted just before the stars merge. In other words, the internal architecture of matter at nuclear scales can leave fingerprints on ripples in spacetime detected billions of light-years away. The first confirmed detection of gravitational waves from a neutron star merger marked a turning point in astrophysics. For the first time, scientists could listen to the universe as well as see it. These signals carry encoded information about the masses, radii, and internal composition of neutron stars. Extracting that information requires detailed models, and nuclear pasta plays a subtle but essential role in those models. Ignoring it would be like trying to understand earthquakes without knowing the structure of Earth's crust. Beyond gravitational waves, neutron star mergers produce intense flashes of electromagnetic radiation and heavy elements. These events are thought to be responsible for creating many of the elements heavier than iron, including gold and platinum. During the merger, matter is torn from the stars and ejected into space, where it undergoes rapid nuclear reactions. The behavior of nuclear pasta under extreme strain may influence how much matter is ejected and how it is distributed, subtly shaping the chemical evolution of galaxies. There is also the question of what happens to nuclear pasta when a neutron star collapses into a black hole. In such a scenario, all known structures are ultimately destroyed, crushed beyond recognition by gravity. But before that final moment, the star's internal layers experience dramatic changes in pressure and temperature. Nuclear pasta may melt, rearrange, or transition into entirely different phases of matter. These transitions could generate distinctive signals, perhaps detectable in future observations. This leads to one of the most tantalizing possibilities in modern astrophysics, that nuclear pasta might serve as a probe of fundamental physics. The conditions inside neutron stars are so extreme that they test theories and regimes unreachable on Earth. By studying how nuclear pasta behaves, scientists can place constraints on the strong nuclear force, the symmetry energy of nuclear matter, and even the behavior of particles beyond the standard model of physics. Some researchers have speculated that exotic particles or new forces could subtly alter the properties of nuclear pasta. If such effects exist, they might reveal themselves through discrepancies between observed neutron star behavior and theoretical predictions. In this way, a strange, unseen material deep inside dead stars could offer clues about the deepest laws governing the universe. Despite these possibilities, uncertainty remains a defining feature of nuclear pasta research. Observational data are limited, simulations are computationally expensive, and theoretical models depend on assumptions that are difficult to verify. This uncertainty is not a weakness, it is a driving force. It motivates new experiments, new observations, and new ways of thinking about matter under extreme conditions. One of the most intriguing aspects of nuclear pasta is how it challenges our definitions. Is it a solid, a liquid, a crystal, a gel? In many ways, it is all of these and none of them. It exhibits long-range order like a crystal, yet it can flow and rearrange over time like a viscous fluid. It resists deformation like a solid, yet lacks the regular lattice structure we associate with traditional solids. This ambiguity forces physicists to rethink how phases of matter are classified. This rethinking has implications beyond astrophysics. The study of complex phases like nuclear pasta feeds into broader efforts to understand emergent behavior, where simple interactions give rise to unexpected structures. From neural networks to social systems, emergence is a unifying theme across science. Nuclear pasta stands as one of the most extreme and elegant examples of this principle in action. There is also an emotional resonance to nuclear pasta that should not be overlooked. It represents humanity's attempt to comprehend phenomena far beyond our sensory experience. We name it using everyday language, drawing on familiar images. Not because it trivializes the concept, but because it helps bridge the gap between the known and the unknowable. By calling it pasta, we make the alien slightly more approachable, even as we acknowledge its true nature as something utterly unlike anything on Earth. As observational technology improves, the indirect evidence for nuclear pasta may grow stronger. More precise measurements of neutron star radii, better gravitational wave detectors, and improved neutrino observatories will all contribute pieces to the puzzle. Each piece will refine our understanding, narrowing the range of possibilities and bringing us closer to a coherent picture of matter at nuclear densities. Yet it is unlikely that nuclear pasta will ever lose its sense of mystery entirely. Even if future theories describe it in exquisite detail, its existence will remain tied to environments we cannot directly access. It will always be inferred rather than observed, calculated rather than touched. In this sense, nuclear pasta embodies the frontier of human knowledge, where certainty gives way to probability and understanding is always provisional. As we approach the end of this journey, one final question looms. Why should we care about something so distant, so inaccessible, and so abstract? The answer lies in what nuclear pasta represents. It is a reminder that the universe is capable of structures and behaviors that defy our expectations. It shows that complexity can arise even in the most extreme hostile conditions, and it demonstrates that by following the trail of evidence, wherever it leads, we can uncover truths that expand not just our scientific understanding, but our sense of wonder. The story of nuclear pasta is not just about neutron stars. It is about the human drive to explore, to model, to imagine, and to understand. It is about pushing the boundaries of knowledge even when those boundaries lie buried beneath kilometers of ultra-dense matter, inside objects that challenge the very meaning of existence. And it sets the stage for a conclusion that brings this cosmic mystery back to us, here on Earth, and asks what it ultimately means. As the story of nuclear pasta comes full circle, it begins to feel less like a strange footnote of astrophysics and more like a quiet revelation about the universe itself. Something so dense, so hidden, and so far removed from human experience ends up reflecting patterns we recognize, shapes we name, and principles we encounter across nature. This is not coincidence. It is a reminder that the laws governing reality operate consistently, whether in the softness of biological tissue or in the crushing depths of a neutron star. Nuclear pasta exists because the universe is efficient. It does not choose complexity for beauty or novelty, but because complexity is sometimes the most stable solution to competing forces. When attraction and repulsion, pressure and resistance, balance at the edge of collapse, matter does not settle into simplicity. It stretches, folds, and interlocks. In that sense, nuclear pasta is not an anomaly. It is the natural outcome of physics pushed to its limits. What makes this realization powerful is how far removed nuclear pasta is from anything we can manipulate or control. We cannot mine it, we cannot shape it, we cannot even observe it directly. And yet, its existence influences real, measurable phenomena: the spin of neutron stars, the way they cool, the signals they send across the universe when they collide. Something utterly inaccessible still leaves a mark on reality that reaches us, quietly but unmistakably. This challenges the way we think about relevance. In everyday life, relevance is tied to proximity and utility. Nuclear pasta has neither. It exists light years away, buried beneath unimaginable pressure, serving no practical purpose for humanity, and yet it matters. It matters because understanding it sharpens our models of the universe. It matters because it tests our theories under conditions we can never reproduce. And it matters because it reminds us that knowledge does not need immediate application to be meaningful. There is also a humbling lesson here. Nuclear pasta shows that nature does not arrange itself according to human categories. Our concepts of solid and liquid, order and disorder, strength and fragility, begin to blur under extreme conditions. What we call pasta is not playful at all. It is matter at the brink of failure, holding itself together against forces that would destroy anything familiar. In its strange resilience, it reveals how limited our everyday intuitions truly are. At the same time, the story of nuclear pasta is deeply human. Faced with something so alien, we reach for metaphors we understand. We name it after food. We describe it in shapes we can visualize. This does not diminish the science. It makes it possible. Without language and imagery, concepts like nuclear pasta would remain locked behind equations, inaccessible to all but a few specialists. By translating the incomprehensible into the familiar, we extend understanding outward. As research continues, nuclear pasta will likely evolve from a curious prediction into a cornerstone of neutron star physics. Better gravitational wave detectors, more sensitive telescopes, and improved simulations will refine our understanding. Some questions will be answered, others will deepen. Perhaps new phases of matter will be discovered, stranger still than pasta. Perhaps nuclear pasta itself will turn out to be more dynamic, more disordered, or more influential than we currently imagine. Yet even if every detail were someday mapped and classified, nuclear pasta would not lose its significance. Its true value lies not only in what it is, but in what it represents. It represents the idea that the universe is richer than our experience suggests, that reality continues to surprise us, even in places we cannot reach, and that knowledge advances not only through direct observation, but through inference, creativity, and persistence. There is something quietly poetic about the fact that one of the strongest materials in the universe exists only inside dead stars. Objects that have exhausted their fuel, collapsed under their own gravity, and ceased to shine still harbor structures of extraordinary resilience. In death, these stars reveal a hidden architecture, a final testament to the power of physical law. Nuclear pasta is part of that testament, a reminder that endings in the universe are rarely simple. For the viewer, this journey through nuclear pasta is an invitation to look at science differently, not as a collection of facts, but as an unfolding story. A story where questions lead to deeper mysteries, where answers open new frontiers, and where even the most abstract concepts connect to the behavior of the cosmos itself. It is a story that does not end with certainty, but with curiosity. And perhaps that is the most important takeaway. Nuclear pasta teaches us that there are realms of reality where imagination and rigor must work together, where we rely on mathematics to see what our eyes cannot, where patience is essential, because progress comes slowly and indirectly. In a world that often demands immediate results, this kind of knowledge stands apart. So the next time you hear the phrase nuclear pasta, remember what it truly signifies. Not humor, not exaggeration, but one of the most extreme forms of matter ever predicted. Matter shaped by gravity, forged by nuclear forces, and hidden inside stars that challenge the boundaries of existence. Something unseen, unheard, yet undeniably real. If you have stayed until this moment, you have followed matter to the edge of physics and beyond intuition. And the universe still has more to reveal, because for every strange structure we uncover, there are countless others waiting in places we have not yet learned how to imagine.